How's it going? Welcome to day 9. It's Advent Code. We're doing stuff. We're making Elm happen. I'm popping out from the side of the video. You never know what's going to happen next here. Hey everyone, I'm Ryan. We have been doing Advent of Code for 8 days. For those of you who aren't familiar, every day in December, 2 coding challenges come out. And it's like every 24 hours. And about 7 minutes ago, day 9 just came out. So we have been doing all of this in Elm. This was our puzzle answer from the last episode that I didn't clean up because I'm a big doofus. But basically, Elm is a language that compiles to JavaScript, so it's great for web development. And we have been doing a bit of functional programming and just kind of taking in the Advent Code puzzle inputs, and then one step at a time, we've been turning them into the solutions. So all these videos start with me giving just a brief introduction and then diving into the problems. I haven't seen any of these ahead of time, and we're gonna see what day 9 brings. There's some elves. They're trying to collect stars. They're in a jungle, so the puzzle's gonna have kind of a weird theme to it. Let's check it out. All right, day 9, rope bridge. This rope bridge creaks as you walk along it. You aren't sure how old it is or whether it can even support your weight. It seems to support the elves just fine, though. The bridge spans a gorge, which was carved out by the massive river far below you. You step carefully. As you do, the ropes stretch and twist. This is intense. You decide to distract yourself by modeling rope physics. Nice. Maybe you can even figure out where not to step. Consider a rope with a knot at each end. These knots mark the head and the tail of the rope. If the head moves far enough away from the tail is pulled towards the head. Due to nebulous reasoning involving Planck lengths, you should be able to model the positions of the knots on a two-dimensional grid. Then, by following a hypothetical series of motions, which is our puzzle input, for the head, you can determine how the tail will move. Due to the aforementioned Planck lengths, the rope must be quite short. In fact, the head and tail must always be touching diagonally, adjacent, and even overlapping. Both count as touching. And even overlapping. Oh, I see. So if the head is ever 2 steps directly up, down, left, or right from the tail must also move 1 step in that direction, so it remains close enough. So, got it. So if we go from TH to TH to TH, this is weird, man. Okay, got it. So if H moves to the right, T will trail behind it. Okay. Otherwise, if the head and tail aren't touching and aren't in the same row or column, the tail always moves 1 step diagonally to keep up. What the heck? So if H and T are diagonal, if H moves up, T moves diagonal and up. If H moves right, T like hops on the row and then goes with it. Weird. You just need to work out where the tail goes as the head follows a series of motions. Assume that head and tail both start at the same position, overlapping. For example, R4, U4, L3, D1, R4, D1, L5, R2. This series of motions moves the head right 4 steps, then up 4 steps, then left 3 steps, then down 1 step, and so on. After each step, you'll need to update the position of the tail if the step means the head is no longer adjacent to the tail. Visually, these motions occur as follows. Okay, so H covers T, so then R4 means it moves over 1, moves over 2, moves over 3. Got it. So it kind of trails behind it. And S is the starting position. You go up 4. Got it. It's going to go up. It's still adjacent. It goes up again. Then T goes behind. Got it. Looks like in all these instances, T is just wherever H was last turn. and that only moves if h is more than 1 away. So like when h moves here, t just goes where it was. H moves here, t just goes where it was. H moves here, t goes where it was. Got it. Okay. So this is just like a little simulation that's helping us understand the movement of the tail. So you can kind of see that there's like a little bit of a delay before the tail starts to drift behind. Okay. This is great. All right, so when you do this, R2, oh, because we were going left, the head covers the tail. After simulating the rope, you can count up all the positions the tail visited at least once in this diagram. S again marks the starting position, which the tail also visited. The hash marks other positions the tail visited. So there are 13 positions the tail visited once. So 3, 4, got it. So 12 hashes and 1 S. Cool. Simulate your complete hypothetical series of motions. How many positions does the tail of the rope visit at least once? Dang. Okay. This is crazy. This be crazy. So this is our example input. We're just going to start at 0, 0, I guess, with the head and the tail. Okay, so let's start with our puzzle input, and let's see how we do. So if we do this, all we're doing is we're taking our puzzle input, we're turning it to a string here, and then we're printing it out. So step 1 is going to be turning these strings, the string into a list of strings, so that each one of these represents a single instruction. And then what we can do is we can turn these into instruction. So we're going to just parse that string and try to get maybe a instruction from it. So each instruction, it has a direction, and it has an amount. Okay, so what's a direction? A direction is either up, down, left, or right. So up, left, right, or down. So those are the 4 possible directions that we could be in: R, U, L, D, all those. So what we want to do is we want to say to instruction. This is our raw input string. So each line we get. So R space 4 is one of these. So in the case where string dot words, so this is going to break up each string into spaces. We're going to get a letter. In the case where we get a letter and a number, so these are both strings technically, so I'm just going to call that this. So if we split up that word by space, hopefully we're going to get these 2 things. And what we're going to do is say in the case where the number string, in the case where string.toInt is just a number with the amount that we move, we're going to say, oh yeah, that's right. So we're going to make sure that, oh, that's right. We're going to turn the letter to a direction also. So I'm going to use a maybe map 2. So maybe.map2. I'm going to use instruction as a function here, as a constructor. And so what this is going to do is it's going to let me say to direction, letter, and then string int to number. Everything else, this is invalid input, so we're just going to say nothing. And then all I'm missing here is that if you give me a letter, maybe I can give you a direction. Maybe this doesn't work. Maybe you gave me an invalid string. So all we're going to do here is say in the case where the string is U, then it's just up. And in the case of R, it's going to be just right. We've got left and down. So I typed that pretty quick. See if this turns from strings into instructions. Oh, and I have to handle the case where it's something else. And for any other string, we want to do nothing. Great. Okay, so let's take a quick look at what we had before we ran this. we had R4, U4, L3, D1, and then after running this, we had like really nice values that we could work with. So the amount is 4, the direction is right. So step 1 of just parsing these to a list of instructions worked great. So this is list of instructions, list of strings. I'm going to be going a little bit fast in this video. If this is too fast for you, you should definitely check out days 1 through 8, where I was a little bit slower to explain like what's list.filtermec, what's string.lines. Hopefully it'll still be easy to understand, but just wanted to let you know that this video is a little bit quicker than the other ones. Ultimately, because I really want to get this puzzle solved, and I want to do it in a reasonable amount of time for the video not to take too long. Okay. So we have a list of instructions, and then we also have a position of our head. We have to worry about the position of our tail. They're both going to start at the same spot. And then we need to keep track of basically the path that the tail has been on so far. So what I'm going to do is I'm going to represent all that stuff with the model. So I'm going to say these are instructions. And what we're going to do is we are going to perform each instruction. We're going to use a list.fulldel. We used this in a previous video, but what this is going to do is this is going to take a function, perform instruction. Perform instruction is going to take one instruction at a time. So maybe that's move up 4 or move down a certain amount. And then it's going to take something called a model. And a model is what we want to define, basically the state that we want to keep track of. So we care about a few things. We care about the coordinate for the head. We care about the coordinate for the tail. I think the easiest way to track the motion of the tail is going to be to keep track of the last coordinate for the head. Last place, I guess last for head. This will make more sense in a little bit. And then ultimately we have like our set of coordinates that the tail has traveled. So travel path. So this is our model that we're going to keep track of. And ultimately this thing's going to keep looping over and over again until we have like the final state. So it's going to start with the initial states. Let's use the init for that. What I'm going to do is I'm going to define a init, which defines the initial state of our model. So initially head is going to be at 0, 0. The last coordinate for head. So like where head was last turn, we can also say that's 0, 0. The tail is going to be at 0, 0. And then the travel path is going to be a set, but we're just going to have a single item in that set. It's just going to be 0, 0. So all these 0, 0s that you're seeing, these are x and y coordinates. So when we move up, we're going to subtract from our y. When we move down, we're going to add to our y. When we move right, we're going to add to our x. And when we move left, we're going to subtract from our x. So coordinate equals it's an int. So that's what a coordinate is. This is going to keep track of everything. Perform instruction. Okay, so we've got each instruction. Each instruction is going to have an amount and a direction. So I'm just going to destructure that here. And what we need to do is we need to return the model after we perform the instruction. So if I compile this, it's going to give me some errors about not importing data types. We don't need a dictionary. We used that in the last puzzle, so the import's still there. But what you'll see here is that we simulate the whole thing, and because we don't change anything, we're not updating the model. So if I just did a quick debug log to kind of show you what I'm talking about, oops, this will print to the console each instruction one at a time. So if I wanted, I can just call this instruction. So if I run this, you'll see that nothing's changed, but we're actually running each instruction one at a time. And this is printing from bottom to top. The things at the top are actually the ones that run last. So we're running through instruction one at a time. So if you look here, you see direction amount 4, that's right 4. This one's up amount 4, it's up 4, left amount 3, and so on. So what we need to do is we need to look at the direction to determine how much we're going to change the position of head each turn. And then we're going to basically keep going until the whole thing's done. So this loop's going to keep running. It's going to return the new state of our like little simulation here. And then the next time it comes in, that new state's going to get passed in. Keep looping. So all I'm going to do here is I'm just going to do a list.take1. This is a temporary thing that I'm going to do to make it so that we only simulate one direction. So you'll see there's only instructions only printed out once, and the output is still the same as our initial state because we're not changing the model at all. So just to make sure that we are moving the head to the right 4 times, here's what we're going to do. So we have 4. So for our direction, we have right. Our amount we have 4. What I'm going to do is I'm going to say delta. I'm going to call it a vector. It's really the same type as coordinate, but a vector is going to be like basically the change here. So the vector might be like -1, 0, for example. So what I want to do is for each direction, I want to see how each direction affects the movement of the head. So toVector could take a direction and return the vector. So all we're going to do here is say that based on the direction we get, in the case where the direction, the dureaction is up, we want to keep the x unchanged at 0, but then we want to subtract 1 from the y. So I just want to use this pattern to determine like, to turn these into like numbers that we can do math with. Whereas left, we're going to go -1 in the x direction and 0 in the y because we're not changing the y direction at all. And then finally with right, we're going to go 1 positive in the x direction, and then we're going to go negative here. Or we're going to leave the y alone because we're not doing anything. So each time we tick through, so we've got this vector here. So delta is going to equal, and I'm going to say toVector, and I'm going to pass in the instructions direction. So hopefully we'll see, because the direction is right, if we just do a bit of debug logging here, and we say, hey, what's the delta? Hopefully what we'll see is this 1, 0 gets printed out. So let's run that. And sure enough, we get 1, 0. So that's printing because this is the delta when we pass right in as our argument. So what I need to do is I need to call this instruction multiple times, but each time I want to basically reduce that delta by 1. So I want to move it right, do the simulation, and then call perform instruction again. And we're just going to kind of repeat that over and over again. So we also need to do this one step at a time because each time we take a step, we're going to want to check is the tail, or like are the tail and head adjacent? And if so, we're going to move the tail to the last coordinate for the head. So that's it. So I think what we want to do is we want to have a function that's like move head. So that'll take in, I guess it'll just take in a delta, the coordinate, and return the new coordinate. So move will take in our delta. I'm just going to move this outside here so we can deal with it out here. So this is going to take in our dx, dy, and it's going to take our current x and our current y, and it's going to return basically the new position, which is x plus our change in x, our dx. That's like a math thing. They put they put d in front of changes in case you haven't seen that before. So this is going to simulate like one delta. And so what I want to do is I think inside of this, I want to do a loop also, where we just keep looping and updating the head, updating the last coordinate for the head, updating the tail, updating the travel path. So, so update model after delta. Could take the delta, it'll take the model, it'll take the model. And so, like, how does our simulation respond to a single like change in motion? So what we want to do is we want to say we want to take the model. Oops. I guess we can just return a new one. So the current position of the head is going to be move. We're going to give it the delta, and then we're going to give it the old position of the head. The last coordinate for the head is just going to be whatever the current coordinate is. Our tail, new tail position, this is going to be dependent on a calculation that we're going to need to do. And then finally, travel path is going to be whatever set we had before, but we're going to insert the new tail position. Sets eliminate like duplicates. So if we've already visited the square, it's not going to like count that twice, which is why I chose a set for the coordinates here. Model.travel path. So all we need to do is make sure that new tail position is defined. So new tail position. What we're going to do is we're going to say if, I'm going to call this the new head position. New head position. I should probably just say coordinate to be consistent. New head coordinate. We're going to call it that instead. New head coordinate is always going to move no matter what. This will be new head coordinate. This will be new tail coordinate, which might not have changed it. It's going to depend on the logic here. So how we're going to perform the logic is we're going to say, okay, if is adjacent, the current position of the tail and the new position of the head, if these are adjacent, we're not, new head coordinate. If these two are adjacent, then we're not going to change where the tail's at. We're going to leave it alone. Otherwise, we are going to make the tail go where the head was last. So where the head was last is just model.head. So if I compile this, Elm's going to complain. It's going to say, hey, what the heck is delta? You said vector, I think is what I said before. So I'm going to just change that to delta. I think it's a little bit easier to read. And then it's going to say what's vector. Sorry, made that up. And then it's going to say what is adjacent. So we didn't define what is adjacent is. So is adjacent will take two coordinates. And give us a true if they're touching. So there's going to be like x1, y1, and there'll be an x2, y2 to represent the positions of each coordinate. So two cells are adjacent if the absolute value of x2 minus x1 is less than or equal to 1, and when we subtract the y's, that's also true. So for example, we're just going to add a bit of comments here to make sure that we've got the math right. If we're at 0, 0, if we're saying, are these two things adjacent? Is adjacent 0, 0, and 0, 0. We're going to do x2, 0, minus x1. So that'll give us 0 minus 0. Cursor's in the way. The absolute value of 0 minus 0 is going to equal 0. So we're going to do that. We're saying if this is true and this is true. And so what we'll get is, if this is less than equal to 1, and this is less than equal to 1. A little bit of a different syntax here so we can kind of understand what's going on. So the absolute value of 0 minus 0 is still 0. 0 less than 1, and 0 is less than 1, this will return true. So these two are adjacent. On the other hand, if we have something like this, where we have things that are 2 away, what we're going to find is that 2 minus 0 is 2, and 2 is not less than 1, so the first condition is going to fail. If we do the same thing with 1, 1, so like a diagonal, what you're going to see is 1 minus 0 is 1, which is less than or equal to 1, and 1 minus 0 is 1, which is less than or equal to 1. And if we did something like, if we made this 2, even though this first thing has a distance difference of 1, the second one is too far away, so it's like up 2. So those are not adjacent. So this is how we implemented our adjacent function here. Okay, I'm going to compile again. It doesn't know what abs is. Oh, math is probably not. I think it's just basics.abs, but I don't think we need to import basics. Cool. And then we call this new tail coordinate. This is compiling, but I'm not simulating this once per amount. So remember, the instruction has an amount and the instruction has a direction. What I need to be doing is for each delta, I need to simulate that however many times the amount said. So what I'm going to do is I'm going to say if amount equals 0, then we're just going to return the model. We're not going to do anything else. We are going to need like a performer thing here. So simulate step. Simulate step. This is going to take an int. This is going to take a model. Count. So I'm going to move this in here. So the count is 0. Then we're just going to return whatever model we have. So I'm just going to call that model. Otherwise, what I'm going to do is I'm going to simulate the step where the count gets decreased by 1. This is just a little recursive function that we're making. And we're going to update the model. So update model. After delta, we're going to pass in the delta we have. We're going to pass in kind of this model underscore. So I call this model here. If we want maybe to make it a little bit clearer and not have the underscore, I'm going to do this, and I'm just going to move simulate step inside here. So this is a recursive helper function that we have. And all it does is it takes in a model, it does this, and it keeps decreasing the count and then simulating the model until we eventually hit this case, in which case it's done simulating. So simulate step is going to take the instruction amount. It's going to start with the delta, because that's the first argument. Then it's going to take the instruction dot amount, and then it's going to take in the model, which we get from here. So I think if I run this, getting close. Oh, I forgot to pass in the delta again. So there we go. Okay, so after moving right 4 times, our head is at 4, 0. The last coordinate we were at is 3, 0, and our tail is right behind us at 3, 0. And all the paths that the tail has traveled is 0, 1, 0, 2, 0, 3, 0. So let's take a look at this first simulation. At the end of this, we got 0, 1, 0, 2, 0, 2, 0, and 3, 0. So let's try it with 2 instructions and see if it still works. I'm gonna get rid of some of these comments here. So after we take 2 instructions, the head should be up at 4, 4 because we moved to the right 4 and then up 4. Up is negative, right? So yeah, -4 is correct. We moved to the right 4 and then up 4, and since up is negative, it's going to be -4. So then we think about where the tail went. This is the important part, is we get 0, 0, 1, 0, 2, 0, 3, 0, and then we don't get 4, 0. The next step is actually 4, negative 1. The order of the set gets sorted by value, so you're going to see that these kind of are moving around. But we know we're doing the right thing because the tail is in the right spot at the end. So what I'm hoping to see at the end is when we're done with this whole perform instruction loop, what we can do is we can get the travel path. That's going to be the set, and then all we need to know is the set size. So the set size is the answer to the puzzle. So it said after we did all this, after we did the whole thing, it's saying what, how many positions did it visit at least once? And the answer was 13. So hopefully when I take off the limit on the instructions and run the full program, we get 13 on the right. Whew, good. That's good news, because if we don't, I had a bunch of debugging to do. So I think we're in good shape. So I'm gonna save this. Every day we do these, I take a copy of the link and I put in the video description below. If the links aren't working, let me know. Shout out to a viewer on day 7 for dropping a comment and letting me know that the links were wrong. I accidentally left in day 6's links. So those are fixed. So please do let me know if the links don't match. Great. So this is with the example input. I'm signed in to Advent Code, so I have kind of a unique puzzle input for mine. So what I have here is going to be a different answer than what you might get if you try this on your own. Sign in with your own GitHub or whatever. So I got 5883 is my answer. And that's right. Okay, this is good. Hopefully we don't run into performance issues. We'll find out. That's the right answer. You're 1 gold star closer to collecting enough starfruit. Okay, great. All right, so part 2 is a little twist on the problem, and hopefully we're gonna be able to reuse a lot of our code, but let's see how it goes. All right, part 2, a rope snaps. Suddenly the river is getting a lot closer than you remember. The bridge is still there, but some of the ropes that broke are now whipping towards you as you fall through the air. The ropes are moving too quickly to grab. You only have a few seconds to choose how to arch your body to avoid being hit. Fortunately, your simulation can be extended to support longer ropes. Rather than 2 knots, you must now simulate a rope consisting of 10 knots. Oh wow. 1 knot is still the head of the rope and moves according to the series of motions. Each knot further down the rope follows the knot in front using the same rules as before. Dang, okay, so before we had a head and a tail, now we have like a list of these knots. Using the same series of motions as the above example, but with the knots marked H1 through 9, the motion occurs as follows. So H, 1, 2, 3, 4, 5, okay. It kind of looks like that. Wow, this is crazy. So H goes to up, 1 goes up. This is weird. 2 isn't where 1 used to be, is it? Okay. So when this one goes up, so this one makes sense to me. As H moves, H moves, H moves, one at a time. Each knot in the rope is kind of moving. When I go up 1 and up 2, I would have expected that 2, 3, and 4 would have followed that path. Confused by that. Why are all 3 of these jumping up? Super weird. I don't think I modeled the first part right if that's how it goes. R covers S. Oh, this is weird. Okay. Tail 9 visits 36 positions, including S, at least once. Simulate your complete series of motions on a larger rope with 10 knots. How many positions does the tail of the rope visit at least once? So I'm looking at this puzzle input and I'm like worried because before what I was saying was that the tail is going to go where the head was previously, or what the knot before it was previously. But now I'm looking at this and I don't think that's correct. So I don't think my motion is accurate. I don't think it goes to where the thing was. So that's true for H, right? 1 is always following behind H. But 2, oh, because 1 goes diagonal. 2 needs to go adjacent to it. So if the delta is 1, 1, then this delta is 1, 1. Oh, I think I just apply the same delta. I think that's how it works. So rather than me saying it's the position of the last puzzle, let me just come back to this last puzzle and see if we get the same answer by changing one line. So rather than saying we have the last coordinate for the head, let's pretend we never did that. Or sorry, let me make sure that this compiles and gives me 13 again. So 13, that's good. I'm going to say forget the last coordinate for the head. This actually might simplify our equation here by a lot. So forget the last coordinate for the head. What if this was just move delta on model.tail? Would this still give us 13? It gives us 10. Delta to each other. Go back to problem 1. So I'm trying to look at this and understand how I can fix my equation to make it a little bit simpler. So right. This one goes up. I don't want to move to delta. I want to move it. This is confusing to me. Let me take a look at this. This is the part that's really going to trip me up, I think. So let's see if we get a better understanding of how the tail goes. We need to make sure that we have this be accurate. So if the head moves here, the tail moves here, tail moves here, the head moves here. That all makes sense. But if the head moves up, this is the one that we were just saying it goes where it is. Confused about us going over 1 and up 1. If it's already diagonal and we go right, this one follows behind. That's not true for this. So everything in those examples, the tail was exactly where the head was. this? I didn't even need I didn't need the thing to begin with. Okay, so we definitely this is a better solution for part 1 because it didn't need to worry about the last coordinate for the head. We just needed to keep that around. So I mean that was working for the head. What's confusing to me is when the things travel to. So let's just take a look at this. So this all made sense. But then when 1 moved from here to here, 2 ended up moving. So it's like if 1 moves up, 2 moves over 1 and then up. It's like sometimes it moves one way and sometimes it moves another way. And I don't think I have a good understanding of why it moves the way it does. And I think that's going to screw me up. Or I can just try to do it with my current formula and see if that works. Head is ever 2 steps directly up, down, left, or right. From the tail must also move 1 step in directions that remains close enough. Here's what I'm going to do. I am going to remodel part 1. Instead of using a head and a tail, I'm going to use a list. So I'm going to say the size is, I guess I don't even need a size. Who cares? All right, so this is going to be my rope. And rope is going to be a list of coordinates. So really it's just going to be list.repeat 2 of these. So we're just gonna try to get 13 again for the 2 example, and let's see if we can get this to work. So I'm not gonna worry too much about this. So each item in the rope is a knot, and that's like the position of the knot. So what I want to do is rather, if I compile, I'm gonna get all kinds of errors saying what's head, what's tail. So what I'm gonna do is I'm gonna say this is gonna be the new rope. New tail coordinate is going to be, if we go to the end of the list, what's the coordinate that we get? So new rope. Let's go get the new. So how the new rope works is we're going to loop through each item. So list of coordinates. We're going to take model.rope, which is already a list. We are going to I feel like the first one always moves. A smaller rope of head, tail. So head is always going to move. We know that much. So move delta head. And then we need to basically get the new, we need to update the rest of the tail. So for each one of these, we're going to say if it's adjacent, we're going to move it. And if it's not adjacent, we won't. So list.map. I want to do a list fold here. I'm going to go left to right. This is going to take an A. It's going to take a knot. This is going to take a tail. Previous list. Previous. This is going to be the new rope, I guess. I'm just doing my best. Previous in the list. Initially, case where model.rope is empty, I can't do anything. I have nothing to simulate. But in the case where I definitely have a head and a tail, what I want to do is I think I want to use the head and tail. And I want to fold each item in the rope. So I think I want the full rope. Model dot rope. I think I always want to move the head. Sorry, I always want to move the head. And then I want to put that in front of this part. And this is like the confusing part that's kind of hard to talk through. And this is gonna move tail not. I don't know. This is tricky. Sorry for the confusion, everyone. Move tail not. It's gonna take in coordinate and a list of coordinates. It's gonna take in a coordinate again. So it's looping through each item in the tail. It's gonna give me the updated tail. So I think this will be empty initially, and then we're gonna slowly kind of build more values onto it. I could be a genius, or I could be totally just way off. Like it's one of those puzzles where I'm like, I don't know. This might not end. Move tail no? Sorry, move tail not. I must have typed that while I was saying no, huh? Okay. So coordinate. This is the current. This is the previous. And then this is the list so far. So what we want to do is based on the previous, we want to run this logic. So this is going to be the new coordinate for them. So the reason I did all this crazy stuff is I want to take the list so far, and at the end of it, I want to put the logic that we had here, except I don't want it to be specific to head and tail. I want it to be specific to, what was the previous thing that we had? This is going to be, I guess, like the new, I guess new is right. So we're going to take this. This next is probably current, previous, and next. So the next coordinate for this specific knot, it's still going to be a coordinate. We're going to say is if the current is adjacent to the previous, we're going to leave the current alone. We're not going to change it. Otherwise, I mean, the old logic would say put it where the basically the guy in front. So the rope in front. Not in front of me. This is going to be current, not. Next current. I guess this is like the updated current knot that we're dealing with. I keep renaming these to try to make it clear, but I understand if that's confusing to people. I apologize. All right, updated knot. Updated. Updated current knot is referring to itself because I'm a big doofus. These should both be current knot. Great. So then this whole thing returns a coordinate and a list of coordinates. All we care about is just the list at the end. So I'm going to do this. I'm going to put this in parentheses. Elm format, forgive me, for I have sinned. And then model.head, it doesn't know what that is. Okay, and then these are not used anymore. New tail coordinate, doesn't know what this is. Okay, and then the new tail coordinate, if we have the new rope, it's always going to be the last value of the rope. So if I have a list of coordinates, So the new tail coordinate, if you give me the new rope, you reverse it and you grab the first item. It's possible that we have nothing in our rope. That's possible. So what we're gonna say is new tail coordinate, maybe dot map, new tail. We're gonna insert that into our existing travel path. And then if for some reason we have an empty list, this is a crazy way to write it. Let's just write it the normal way. Just tail coordinate. Oops. Then we want to use set.insert tail coordinate onto the existing travel path. And for whatever reason, if somehow we get like an empty list, which isn't really possible in our current program, but it is possible with the data types we're using. It is possible to have an empty list get passed in, in which case the travel path would not get updated because there's no new coordinate to insert. That gives us 9. Okay. So I don't think this is quite it. Let me see if let me just try this with the delta. I don't think this is right. So back to going back to the basics, let's just start with our first thing and see where this starts to go wrong. So I have all these instructions. Let's just start with the first instruction. So 2 is the answer. And I don't think that's right because amount right, the delta is 1, 0. I call simulate step. Move the tail knot. As long as I have items in my rope, I'm going to move them. So I take the head. I'm going to move the tail knot. Not in front of me. I'm adjacent. I'm not going to move. Do this. This so far will build up the current, and I'm going to also see what the model looks like. So I'm not going to quite get into this. So I do have 4, but then this one says 2 because I think it's comparing. Yeah. So the knot in front of me. So this is the issue. Let's give this a type, okay? So this is going to be the mini model, okay? We're going to call this the mini model. And what it's going to store, it's going to store the knot in front of me. So this is going to be where the knot moved to. So this is a coordinate. Not in front of me, old, or like the last position. Last position. Let's call it previous. Previous, current, and then we're going to have the list so far, which is list of coordinates. Okay, so this is our mini model. We're going to work with this instead. After the knot in front of me is moved, we're going to ask, is this? This is so verbose. I'm just chuckling because this is crazy. I've got to say it with my mouth. The knot in front of me's current position is adjacent to the current knot, then I do not move. But if not, I'm going to move with the previous. It's important that these are different values, and I wasn't thinking about the current and next. So the previous value is the head. The initial value of list so far is this, and then finally the knot in front of me the current position of the knot in front of me is after it's moved, because that's what I need to compare against. Hopefully, this will give us 0, 1, 2, 3. Oh, and then tuple second. So instead of tuple second now, I do dot list so far. So fart. Okay, and then all we're gonna do is we are gonna say that the knot in front of me previous is who I was, because I'm the new next knot. And then we're gonna say the knot in front of me current is where I ended up, so that's where I go. And then the list so far is whatever the heck it was before, but I'm gonna append myself my updated version. Please, oh, I should probably use valid syntax. Okay, I think we'll get back to 13 now. If I get rid of the take one. Okay, we're back to 13. I'm gonna save this. All right, so we're making progress. I'm gonna save this in the video description as 1.5. This is answer 1.5, and we're gonna see if I just bump this to 9 if it's right. I can't be right. That cannot be right. What the heck? Oh, maybe it is right because I don't move much. So it says that for part 2, it doesn't move much, right? So 9 doesn't end up moving more than 2 squares, right? So if we look at this whole simulation, it only visits one position. Be careful. More types of motion are possible. So you want to visually compare this, your simulated rope to the one above. So I'm pretty sure this isn't going to work. Okie dokie. So I'm pretty sure this isn't gonna work. But we're getting closer. I think it's just a matter of simulating the new position based on the delta and based on the. I am trying to come up with an equation that follows what I'm seeing, and I'm struggling. So H1. I think if we get this right, our answer should be 1. Right now our answer is 2. So what I'm going to do is I'm going to keep this input the same, and I'm going to try to I could just print out like each item and just debug it that way. That could be really cool. But what I'm going to do instead is, oh, you know what? That's probably why the program gets so slow. I had all these debug logs the whole time, just printing out stuff over like a bajillion cycles. Okay, simulate step -1, last position, current position. Okay, the thing that's different is calculating the next position for my knot. So this is the part that's going to need to change because I'm 100% sure that this isn't right. What looks to be happening is that it is the last position unless this moves diagonally. If this guy moves up and right, the knot next to him moves up and right. This moves up and right. So this moved up and right, so then this moved up and right. If this moved up and right, then this moved up and right. So what I'm seeing is in the next step, when this moves up again, it's continuing to be in the previous position. And then 3 moved up and right, and 4 moved up and right to match the motion of this. Okay. So I'm gonna use that. So I'm gonna say if they're 2 away from each other. So sorry, if the delta so if the position is more than 2, then I want to match the delta. I don't know how to put that in English, but I'm going to look for an exception to that rule. So H moves diagonally and over 1. Now when it moves left, 1 moves to where it was, 2 moves So 1 moved up and left, and 2 moved up and left. I'm going to go with this, okay? I'm going to say that I've got it right. And what's going to happen is, else if the not in front of me, so the, I guess is adjacent. How this last not moved. If they're adjacent, then I'm going to just move to where it was. Otherwise, I'm going to get the difference. I'm going to call this the not delta, which is a little bit weird. The not delta is going to be this minus this. Find difference. This is like really finding the vector between these two. Oops. And then I'm going to say move not delta current not. And so what it's going to do is it's going to see how far the thing moved, and it's going to return me basically a delta for how much it moved. And that's like the pattern I'm seeing. This could be wrong, but I got to try something. Can't give up, you know, you got to keep pushing forward. So what I'm going to try to do is I'm going to say, all right, what's the delta? It is x2 minus x1. That's how much the x changed. And then y2 minus y1. So when I take that difference, I'm going to add that. I'm going to use move to basically add that difference here. 2 again. I don't think the difference in front of it. Oops. Previous, before and after. Take where I'm at. Let's see. Log. Go back to 2. Oh, it's hard to do this. I also feel like there's like a really like simple like math answer to this problem. Let me make sure that is adjacent is a fair way to do this, because I think that this math is right. It's just a matter of me being a big doofus. So I compile this. 2, I'm hoping to get 1 if my logic's right. Not in front of me. It's like if the distance I traveled is. Let me just take a look at this. So here, each one. Yeah, that's always true, so that's not good. H went up. H went up. So what I care about is if the new position of 1. This is what's so weird. It's like the first one always follows, and then the 2 always follows. Yeah, this isn't right. It's like if the thing moves diagonally, then you also copy it. It's like, did the thing move diagonally is the question. Did move diagonally? Then this, if not, you gotta like copy the difference. It's like, it's weird. it's like this. So if it moved diagonally, the previous to current, it moved diagonally. I need to find the difference, and then just apply that to myself. So let me just compile this. It's gonna be like, what the heck is did move diagonally? Which is a great question. Basically, if I take coordinate 1 and coordinate 2, and I find the difference, dx, dy, find the difference of these two coordinates. And then it moved diagonally if dx is not equal to 0 and dy is not equal to 0. Right? Because if one of them is 0, it moved horizontal. If both of them are 0, it didn't. Oh, that gave me 1. That might do it. This might be the answer. Please, please be the answer. Okay, so now we've got a bigger set that'll hopefully give us a bigger number. So we got 1 for the first test. This one gave us 42. Please be 42. Please be 42. 36. Dang. So what we can do is we can print out the states as we go. This would be a really great way to debug it. After each loop, we can just print out the state. I think this is going to be a really nice way to debug the problem. So we're really burning the literally midnight oil here. So what I want to do is I want to print out. Each time I simulate this, I'm going to print to the console here the value of the grid. Do this well. I don't know if debug log is going to be nice to me, but I've got each instruction. So what I want to do is I want to print the map. I want to see what we get here. Yeah, we're going to print a map. Of model. Oop. We're just going to give it a range. So I think the range here was 4, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So we're going to do a 25 by 25 grid, and we're just going to print this out. Ugh, okay. Print map is gonna. We're gonna debug this thing. It's gonna be sick. I'm smiling because this is the first time I'm excited about this. Okay. This is gonna be the width, the height. It's gonna be our rope. All right, so for each width, what I'm gonna do is I'm gonna build up a string. Stat range 1. I'm gonna repeat W characters. So we're gonna repeat the following character W times. Now we've got a list of 25 dots. I'm gonna do list.index map. This is going to be the Y height. And this. Okay, index map has the Y height. It's gonna have the char. And then we're gonna do the new char, and then do string dot from list. So hopefully this just gives me a bunch of dots. Okay. Debug log. And then we're just gonna say, oh wait, okay, debug log. It's gonna give me 25 dots. Okay, we're doing it. This is crazy. Okay. All right, list dot repeat. We got 25 of these. We are going to list dot repeat that height times. Then we're going to string dot join new lines. Okay, we have it. We have it. We have it. We have it. And let's see if I can. Let's see if I can see this in the console. Garbage. This is not working out for me. If only I had a program literally designed for making user interfaces. Why am I doing it this way? 8 times this gets printed out. Okay. Okay. Debug log string join this. This. Copy this. This is gonna be a trip. Log. Something. We're getting these somewhere. Okay. Oh my gosh. Okay, index map y and char, and then we're gonna take it from a list. I don't know what I'm doing. I don't know what I'm doing here. This is crazy. Let's have some fun because we lost. We lost the debugging game. At least I'm pretty sure we lost the debugging game. What's going on with this? Let's delete that. Delete this. All right, Elm is a language that can render HTML. So what we're gonna do is we're gonna keep a historical record of all the ropes. So history equals an empty list. History is going to be a list sets. Actually, the list does matter. It's gonna be, this is gonna be the history of ropes that we have. When I compile, it's upset because simulate step doesn't account for the history. So what we're gonna do is, we're gonna build up the history one step at a time here. Every time we simulate the step, we're gonna say model history equals model.history plus model.rope each time it comes in. So now we're going to get this crazy list of lists. And what we're going to do is we are going to actually render some HTML to the screen. This is Elm. We're doing everything in Elm. This just makes sense. So this is our model. What we're going to do is we're going to have all this. And we're not going to do debug.toString anymore. Welcome to your first Advent of Code series where we actually use Elm to do things that you might use Elm to do things for. We're going to make a pre-block here. Actually, we're going to make a div. Actually, we're going to make a paragraph. Stop map, view a map. And again, we're going to do 25 as our grid size. What we're going to do is for each item in our history, we are going to view something. So view map This is going to be our bounds, so our width and our height. And then each thing here is a list of coordinates. This is going to print out exactly what you see in Advent of Code. We're going to print this to HTML. It's going to be great. I'm excited. So a map, it's going to have a size. It's going to have the rope at the time, which is just a list of coordinates. And what we're going to do is we're just going to print out a pre with some code. And the text here is going to be that crazy string that we made, right? So this is going to be the string. So if I said hello, you're going to see, because there were how many steps here? How many instructions? Because there were 1, 2, 3, 4, 5, 6, 7, 8. Since there were 8 instructions, we're going to see 8 pre-tags here. And I'm going to do a list.index map. That's going to do is that's going to give us how many times we've run this. Count. So div h3. Just going to do another div here. All this is going to print out is run. It's going to print out the index. Sorry, this is the index. String dot from int index. And we're going to print out some HTML. We're living in the future here. The future is around 2011. There you go. We got hello, hello, hello. This is awesome. And they're monospace. We're living our best lives. Okay, so what we're gonna do is we are gonna use this to help separate things. Okay, so run 0 will look like that. What we're going to do is we're actually going to print out for all these coordinates. What we're going to do is we're going to find the index. The index, we're going to say if the index is 0, we're going to represent the character as an H. So we need to know if you give me a coordinate, I will give you a letter. So we need a lookup. If you give me a coordinate, I'm going to give you a character to print out. So coordinate. How we're going to do this is we're going to try to say dict.get. If we can find a match in our rope knots, which is going to be a dictionary, I promise, then we are going to render that. We're going to make a rope knots dictionary, which if you give it a coordinate, it gives you a character. If we do that, that works. Then maybe dot with default. We're going to say the default character is that dot that you saw before. I'm having fun now because I'm not dealing in text land. I get to write some HTML. So this is going to be a dictionary where if you give me a coordinate, I will maybe give you a character. So rope knots. We're going to take our rope. It's a list of coordinates. We're going to do list.indexed map. And then each index for each knot in the rope will come along with a coordinate. So what we're going to do is we need to say for this coordinate, if I equals 0, then our character is H. Otherwise, we're going to say char. I don't know if there's a char from int. You know what we're going to do? We're not going to use chars. We're going to use strings here. String, string, string. This is that. Very cool. Okay, so we're going to use this. We're going to say H. Otherwise, we're going to say string.from int of whatever integer we get. So if it's 1, 2, 3, 4, all the way up to 9, that's what we'll see. This is going to give us a list of coordinates paired with strings, which is great because we need to turn that to a dictionary. So now we should have a dictionary that if you give it a coordinate, it gives you a string. I need to import dictionary, otherwise my life is going to be very bad. Okay, this should still compile, but it shouldn't show us anything yet because we need to replace this with the grid. You give me list dot
repeat whatever the size of the grid is. So this will be 25. We are going to say range of 0 to size -1. And then list dot map, I guess cat map. This is going to give me my y coordinate. Do list dot range 0, size -1. This will be my x coordinate. List dot map. This is my x. I will give you x and y. That will be a list of coordinates. And what I will do is I will you know what, I'm gonna do this. Stop map. And I'm gonna say lookup. So this will be a list of, so if I have a range of numbers, I have a list of numbers, a number comes in. I say for each number, I want you to give me this. To join this on white space, and then I want you to join this on a new line. Sick. Sick. Okay, we're getting places. All right, so the only thing is that we want to go from the bottom left up. So I think I want to reverse. Alpha, I want to go down, huh? These both reversed. Okay, let's stop first. Sorry for this crazy code. I want to solve this puzzle. I don't care who gets hurt. Ah, shoot. Doing something wrong with these lookups. Maybe I'm not doing something wrong with the lookups. Maybe this visualization is right. I'm just doing it. So it does this, and then I move and it goes in the wrong direction. I think is what my issue is. Really, if I want to keep it on the screen. Where does this thing start? Oh, it starts in the middle. Doesn't help. Okay. Okay. Here's what we're gonna do. We're gonna change size to like the bounds. So we're gonna start at -12, 12. We're gonna kind of center on this. These are gonna be the bounds. Coordinate. Top left X, top left Y. It is gonna be a hell of a video, folks. All right, coordinate. Top right X, top right Y. No, bottom right X. So instead of size, what we're gonna do is we're gonna say starting at the top left Y, going to the bottom right Y, repeat. And going from the top left X, bottom right X, repeat. for doing it. I'm so exhausted by this problem. What the heck? Let's see if our patterns are at least right. Like, it does this. Is this right? Is that what it's supposed to look like? Let's break this apart here. I'm going to snap this, snap that, get this here. This is our... So for run 0, we have this. It's somewhere. I get that the H it should be on the top, but it's not. I think I can fix that with the reverse. I don't know. I'll try. I'll try to do it for you. Great, I fixed it. Okay, so we get the H. H 1 2 3 4 5. So that step's going good. This is actually kind of cool. H 1 2 3 4 5 6 7 8. But this says 9. You 8. This is so close. Oh, this is where we lose it. Okay, so I'm doing everything right except all this debugging is because I repeated 9 instead of repeated 10. I cannot believe it. It's literally because I should have typed 10. If 9 is the last knot, then there should be 10 ropes. This was the bug the whole time. I am convinced. Travel path. Alright, whatever. I'll do this. So, answer. I did all this because I typed in a 9 instead of a 10. This is the most me garbage. At least we had some fun making the visual. Anyway, I'm pretty sure it's going to work. I'm pretty sure I'm a doofus. I'm pretty sure that's why you come back for more content. I did fix the bug. It just, oh my gosh. All right, debug, toString. It's almost 1 in the morning here. It's 12:30. This is not coding weather. All right, answer. We had fun though. We had fun. We built a whole map. Okay, hold on. HTML text. This... That's still wrong, I think. I think it's still wrong. 38, I think it was 36 was the answer. Okay, well, let's go back to simulating it. Good thing I didn't throw everything away. So I think I'm still doing something wrong, but at the very least, we know that I'm not a complete doofus. Well, I am a complete doofus. All right. H. Okay. Good, good, good. This is important. So now we can actually debug this stuff and we can see where I lose the thread. H. What is this? How many dots is this over? 24, 34, 3. So we want to go negative, oh, whatever, doesn't matter. So I go over a bunch. I got that part right. Start. Well, this is probably good. I could also print the start, huh? want to print an S here. S else. This is super hard to read. Oh, I'm blocking the thing. I'm blocking the thing. We're gonna have a real high production quality video today. Now we can see what's going on. This is what's crazy. This is where I start getting wild. I think it's because my delta is 6. Yeah, I think this is it. Delta for the 5 is -4. I just don't understand how this motion is supposed to work. Like this motion's crazy. Okay. So H moves over 1, 2 stays where it's at, and then when it moves, oh come on. Okay, the H moves over 1, the 1 stays where it's at, it goes left because it is far 1 hops up to where it is. The 2 follows suit. 3 is chill. Follows suit. The 3 is chill. The H1. H goes down and left. The 1 stays there. The H goes right 4. Right? Do. The 1 goes where the 2 is. Let's start with this one. So let's start with the simple one. And by simple I mean like part 2. It's got to be like one line of like logic. Like it all comes down to me. I have no idea. I have no idea how a rope moves. Like, do I actually have to know what Planck constants are? Is this actually a thing? Because like I am too stupid for it. I can't do it. I lack the strength. I lack the strength to stand and the will to live. So what we're gonna do, you're gonna print the puzzle after every single step. So history is gonna be granular this time around. So before we were printing out history not frequently enough. What we're gonna do is we're gonna pen the new rope each time. Every single step. Okay, let's figure this out together. Part two. Okay. H1, H1, 2, H1, 3, H1, 2, 3, 4. H. And I could probably lower my bounds here. That'll probably make it easier to debug this. Let me adjust my bounds. Zero, 0, and it's gonna go up to 6, 6. Okie dokie. We have H. All the way thing, and then when I get to the end here, let's run 5. Oh, run 5, it's entering it twice. I don't want to do it twice. I'm gonna do it once in the beginning, and then I don't want to after each perform instruction. I don't want this anymore. I think I just want to give it model 5. up 1. This is correct. This is correct. This is correct. Cuts left. Next. Each one. Yeah, these are all lined up. 4, 5, 6. Cuts over. What's the height? Sorry, I'm just gonna reduce the height by 1 because it's tripping me up that it's not the same as the drawing. Looking at this, that is the same as this. Left 1, nothing changes. The whole structure stays the same. I move left 2. 1, 2, and 3 get stacked. 1, 2, 3 stacked. 4, 5, 6 don't change. Each one, I get 2, 3, 4, 5, and 6 don't change. Go down. Go right. This is all good so far. H covers 2. 1 covers 2. Yeah, that's where I'm at. Okay, so this run 15 is the same as this. 21H, 3, 4. H, 1, 2, 3, 4, 5, 6. Gravel path. The heck, everything's fine. Everyone's good. H is over 3. H is over 3. H1, 3. Let me just skip a bunch all the way to the end here. There's 3, 5, 6. Okay, so that literally did everything that it described perfectly, right? It literally nailed it. All right, be careful. More types of motion are possible than before, so you want to visually compare your simulated rope to the one above. So I literally, everything's fine here. So if we undo back to where we were, 15, negative 12, and I was doing history. The big boys. Okay, so let's go back to this. So initial state, this is 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2. It's 14 to the right. So this is I'm gonna drop 1 on my X. I'm gonna drop 1 on my X. It's pretty cool. Seems pretty seems like a tough guy. All right, 14. In terms of the down, I think I overdid it in downtown. Oops, that's uptown. This is only 1, 2, 3, 4, 5, so let's just do 5. So this is looking more accurate, and then this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's 1 less here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3. Here, I'm going to do it. 1, 3, 5, 7, 9, 11, 13, 15. Okay, so this is literally it. It's the exact same thing. What I need Elm test to run a diff on this for me. So I move right 5. up 8. There's S. I move left 8, and then horrible things start to happen to me. Just horrible things. Like, things that don't make any sense. Like, why would these be stacked? And, like, how am I supposed to know how this happened? So what is over the S? 3 is over the S. 3 is over the S. But for some reason, these are, like, stacked. Even though 4 didn't move. Why would this be a straight line? Refresh this. Is this like puzzle wrong? Am I stupid? How am I supposed to know how that works? Alright, I think I just skipped some important information at the top or something, right? Oh boy. Must always be touching. The head is ever 2 steps directly up, down, or left, right. The tail must also move 1 step in that direction so it remains close enough. The head is ever 2 steps directly. The tail must also move 1 step in that direction so it remains close enough. Otherwise, if the head and the tail aren't touching and aren't in the same row, the tail always moves 1 step diagonally to keep up. You just need to work out where the tail goes as the head follows a series of motions. Okay, so that was a very simple set of rules that I just didn't read because I'm a dumb person. So if the head and tail aren't touching and aren't in the same row or column, the tail always moves 1 step diagonally to keep up. So let's just code it right, because I'm a doofus. So it's not about adding the delta, it's about moving 1 step diagonally, regardless of the delta. So let's just code it the way that the puzzle told me to code it, and then the puzzle will work, right? That's the play. So we have really good visuals to go off of, and I just need to change the thing. So if yeah, so like I'll just use the English that they said when they gave me very clearly how the puzzle works. 2 steps directly, so has moved diagonally. Oh, I think that's what I already had. So if it moved diagonally, we're gonna do something. If not, we're gonna do something else. I have a feeling like the not delta is what I'm doing. So I need to find the diagonal and the direction. So if I'm here and I want to go there, just give me the diagonal, find diagonal in direction, starting from me, current knot, going to the knot in front of me. Yeah, I should just read the instructions. Okay. Find the diagonal in that direction and just move it. So all we're going to do is we're just going to implement a function called find diagonal in direction. You give me a coordinate, an accordiante. You can save so much time debugging by reading. Also by knowing that 10 is greater than 9. Okay, x, y, if my target x, my target. So find a diagonal in that direction. So this is going to assume that we already proved that it moved diagonally. We're going to keep this super simple. And we're going to say if tx is greater than x and ty is greater than y, then positive for both. Oops. Else if tx is greater than x and ty is less than y, then we're going to go greater in the x direction, but less in this direction. We're just going to go boop, boop. Just going to cover the other diagonals. Everything else we're just going to ignore and say that it should never have happened because we never got to this case. All right. So if tx is less than and greater than. Did move diagonally. Not at all with that. They're adjacent. You don't do anything. You don't move. Just want it to be over. I just want it to be over. Move me touching and aren't in the same row or column. The tail always moves one step diagonally to keep up. One step diagonally. One step diagonally to keep up. This isn't the condition I want. This is not in same row or column. Oh. T is da. So tx is greater than x, then 1, 0. Else if it's less than, else if it's less than, else if tx is less than -1, 0. Else if ty is less than y. Lower, I want to go lower, I want to go lower. It's greater than y. Up? No. Is this the answer to my dreams? Is this the answer?
Does it get weird in the corner? It could be over. It could all be over right now. This says 36. We can all go home. Oh.